Okay, so I'm Thevin, and I will present you the paper Creating Accessible Interactive Audio-Tactile Maps and Graphics Using Spatial Augmented Reality on the behalf of my co-author as well. It is mostly about using Spatial Augmented Reality as an authoring tool to create content. So first, maybe to come here and reach a conference, you perform some daily life task. For instance, you look on a map where was a location of the conference. You have a look on the underground and metro line station on a map. And during this journey, you may read the paper about the last virtual reality devices. But how could you do that with visual impairments? So you don't have access to any spatial information when they are represented visually, and you can access the text with text-to-speech, but not to the figure of your paper. So how special education schools do to make content accessible to people with visual impairments? They use tactile graphics to represent spatial information. So this is a raised line map where the ink raised 1 millimeter over the map when it's printed. You can also use mass-scale models or 3D model. For instance, here from a train station. You can use magnet on an iron board to create streets or building in relief and build a map with the students with visual impairment. Or you can draw on German films that raised the line you draw with a pen of 1 millimeter over the paper. But it has some limitations because when it's not the teacher that describes the student with visual impairment what he or she is touching, it will be, the caption will be in brailles, and that have some limitations that audio can overcome. For instance, first, brailles takes quite a lot of room and cannot be resized because it's optimized for the fingertip. And it is limited to braille readers that represent only 20% of people with visual impairments. Also, it is a physical content, and so it's static, while dynamic content can foster the learning. So now I will show some work, because in the HCI community, some work proposed to add audio to make tactile graphic interactive, and so you can use a tablet that will detect the touch behind and put a map, tactile map on the top of it. You can also use an under-table camera that will track tactile tokens and fingers, so you can represent tactile graphics and maps with this way. You can also have objects with embedded electronics that are audio-tactile objects, or you can model in 3D object and add audio annotation, and you will launch the audio annotation using a webcam. But there are some remaining issues. First, most of this system are not designed to be used with all the current classroom contents in the school for people with visual impairment, and they do not provide actually an authoring tool for people without IT backgrounds, so they really hinder the use of the teacher and of the relatives and the family of such systems. So what we did is we do a participative approach, and from the user need, we propose a system. So we augment directly the existing contents of the classroom with audio. So for that, we propose to use Spatial Augmented Reality, or SAR. So it's projected augmented reality, so we keep actually the existing content they use, and then as well can use this content without the system in the usual way. And so we detect the touch, and when the user touch any part of the map, it will provide captions, audio captions. And here, this is our main contribution. We use SAR to create an authoring tool, and we use a touch interaction, so the user can directly draw on the tactile graphic directly with a finger to create interactive zone, and then register and add any audio caption. As we use the same system for making the content audio-tactile and for the authoring tools that enable direct testing of the created content as well. So now some video about how, with some teacher using the system to create content. So here a teacher, she with a finger, she draws the Peloponnese interactive area, and the video projector gives visual feedback about the interactive zone. And for the complete process, here, a teacher draws an area around the tactile city, register the feedback. Lavrio, that is the name of the city, and then the teachers can directly test the content.
Lavrio. Raffina.
So this was really teacher, and we use this content actually in a real classroom. So what are the main features? We can draw with a finger when we create content, shapes. So when we touch anywhere inside the shape, it will play audio feedback, or lines that are represented to use streets, and every time we are close to the line, it plays feedback. And then we can add audio content, or with text that will be rendered by text-to-speech, or directly by a register with a microphone. And then when we touch the zone, we have the audio-tactile content and the audio content that is played. So what look like the system? We use Palard, a Spatial Augmented Reality toolkit that provide aware and API. So for the feedback, we have a video projector that give visual feedback, for instance, about interactive zone. We have speakers that play the audio annotation, and we use tactile maps to make the tactile graphics. And the input of the user are the touch is detected through a depth camera. So when we touch, we detect the collision with tactile graphics, and we use as well, and this camera also detect color markers. So we have interactive wood cards that enable to tangible interaction to select if we want to create a shape, a line, start recording, stop recording, and play the audio feedback, and we can record with a microphone. So here a picture of the system, and we did this follows some previous work. So on the first work, we verified that such audio-tactile content with this system was actually accessible for children with visual impairment. Then in the second study, we provide a graphical user interface authoring tool, and we verify actually it was usable by the teacher, and the created content was accessible for for the students with visual impairment. And actually, for that, we use Inkscape, that is a free vectorial drawing software, so the teacher can directly draw this interactive zone on the top of the picture. And as it was usable by the teacher and accessible to the students, that will be our baseline in our user study we present. Here, and then for this study, we follow a participatory method that you can have more detail in the paper. But actually, it was 6 months design for vision of the prototype. We use that with 6 scenarios of the teachers, and we use that in classroom in 3 countries, France, Greece, and Romania. And we use the system entirely by the teacher in 2 inclusive classrooms with children with and without visual impairment in this classroom, and the result of an online questionnaire answered by teacher and children with and without visual impairment are described in the paper. So after all this design, our user study, our objective was to actually verify the potential of spatial augmented reality to create audio-tactile content. So we propose to compare actually our prototype with a GUI alternative we already demonstrated as efficient in our previous work, that is Inkscape, to have a reference, a baseline. So our first hypothesis was that the participant can rapidly create interactive audio-tactile content with SAR compared to GUI baseline. Here, the time is an important component because if we want the teacher to use it to prepare pedagogical content, they don't need to take so much time every day to create the content for the weeks. So here we measure the time to create interactive zone. And the second hypothesis was that the content creation is possible without requiring any specific technology-related skills. So for that, we tested with stakeholders that actually used Audio-Tactile graphics during their professional life with multiple technological background. I will not describe it in this presentation, but we can talk about that after the presentation, or the details are in the paper. And the last one, we want to verify the content creation is easier with SAR than with GUI baseline. And for that, we use attractive portfolio to compare. So our participant, actually, we did our experiment with 28 participants, 10 male, 17 female, and 1 non-binary participant. The average age was 37 years old. Several participants was cognitive sciences intern, and 5 were working specifically in accessibility for people with visual impairment. 16 participants were from a school for people with visual impairment, and 5 participants were from a braille transcription center. And actually, so we compare the two systems. So here an example of, in videos, a participant creates interactive content with SAR by drawing a zone with a finger, then recording. She uses a
microphone activé.
Basilic Saint-Lucie.
She adds all the captions.
Validation.
And then she verifies it's working.
Basilic Saint.
So here she did with the first system, she annotates a first map in 10 minutes. And then she does the same thing with the graphical user interface baseline when she draws the interactive zone on the picture and then add text that will be rendered as text-to-speech later. So actually we have two counterbalance conditions. One is the first map or the second map that are controlled in terms of number of elements and type of element to annotate between line and shapes. And we have two technological conditions, GUI and SAR condition. So for the SAR condition, the setup is the one I previously presented. Then we as well give a caption to be added to the map, to the participant, and the location of the caption. And for the GUI, we have a computer with keyboard, mouse, and Inkscape open with the image of the background of the map to annotate. So the complete protocol was first introduction and consent form, and then the first system. So all the participants start with 10 minutes to learn how to use every system. We have a familiarization tactile graphics, so they make it interactive with the experimenter. Then they have 10 minutes, and within 10 minutes there's the instruction to create as many as possible interactive elements on the 20 of the map. With the first map, they have to augment. And then they evaluate the content with a satisfaction questionnaire and attractive questionnaire. And then they do the same one with the second system and the second map before regarding personal question regarding personal detail. So what are the results? Here's the results regarding content creation results. So actually, in average, Spatial Augmented Reality was always faster than GUI to create elements. For instance, in average, whatever it is, shapes or line to content, participants require 32 seconds to create a zone with SAR and 57 with GUI. And it's significantly faster for all the elements with SAR. One participant didn't create lines because it was too complicated with GUI. And if we look at the completion, because with SAR, actually people can test the content. So there are a lot of time when they are not created elements, they are just verifying the content. And still, 12 participants created more than 90% of the 20 elements of the map within 10 minutes for only 4 participants for graphical user interface condition. So it is as well, significantly more content is done with SAR. And in average is 17% more per participant. So regarding user experience, this is a portfolio of attractive, and in blue with a square, it's a SAR condition that is rated as desired. And in red with a circle, it's GUI conditions that are between neutral and task-oriented. So actually, regarding this questionnaire, SAR is better and easier than GUI, and that as well what the participants say, they say like P9 say like SAR show like a simplicity of use. P14 said I prefer Palard because as always mastering computer is time demanding to me. P19 says SAR is simple to master, even if you would choose graphical user interface for the higher precision, because actually you can control point by point all the areas. And so for the conclusion, but yeah, it's lacking of precision. It's precise by the 3 other participants. So GUI is more precise, but strategy are done by the participant to avoid the shapes that are more complicated. For instance, curved lines. With SAR, it's simpler, user-friendly, provide pleasure in use, but is less perceived as precise. We can discuss it during the question. The content can be created with GUI without the toolkit because on a computer, but you cannot direct testing the content. As with SAR, the content can be directly tested. You can create the content in classroom with a student as well, but it requires dedicated room. And finally, graphical user interface is a computer, so it's non-environment. The user would prefer to use SAR, but are more confident to use GUI alone. And SAR is playful and embodied, but for now it's quite new. So thank you very much, and do you have any question?
Thank you. Questions? Please raise your hand. I'll start with a question. So this is for the teachers to create content. Once the content is created, it's going to be used by their students, which are non-sighted users, right? Mm-hmm. And has this been tested, or do you guys hoping to test this system with them, with the actual users of the system, as opposed to the content creators are users too, but the actual end users?
Okay, yeah, so this is actually with already tried in 2 other studies the content to verify it was usable by the students. So with the same system, so here it was only on authoring tool. And then actually we use that with people with visual impairment in the 2 classroom. And some people with visual impairment use the same system to create themselves interactive content because we use tangible card to select the component and to draw with a finger. In classroom, actually, we had to add some additional features because there is a lot of students that are putting their hand on the table. So we have to catch what are the finger of leaning arm or not, and to remove it. And it was with Spatial Augmented Reality, the point is when you draw with the finger, actually the offset, when you draw, contains the calibration offset. So when you touch something tactile, you will have the feedback even if there is something there is an offset, while the sighted user will touch the light feedback, the color feedback. So actually it was more usable with the SAR for people with visual impairments than the sighted that will more refer on vision.
Thank you. Do we have any other question? Don't be shy.
Thanks for the great work. I was wondering, do you have any plan to add other sensory data, like for example, like even tactile, not touching the surface, but maybe the object, or maybe other, haptic, like feedback or something like that?
Yeah. So actually, this system allow like color tracking, markers and fiducial markers. So we use it, but we didn't. We didn't evaluate it in the study formally, but we add some object with a fiducial marker on it, so we can annotate it, and it will follow the object. So we use that, for instance, for interactive puzzle. We use that for a building interactive map. So you set a caption for a building, and then you can move it and create map with students with visual impairment prior to visit a place. So yeah, it works with fiducial markers.
Only one maybe comment, maybe you can explore with different like surface quality, because they're very sensitive about their fingertips. Mm-hmm. So I mean that might give a lot of variety of materials you can use.
Yeah. So actually that was also one of the advantage of the SAR for that, because we use that with, for instance, real leaves, while with if you only refer on digital content that is then implemented or printed in 3D or not, then you only have one texture basically, or you have to recreate here. But here we can augment real object with their texture.
Thank you.
Thank you.